Now we are going to talk about something called definite integrals. Okay? Definite means what? The fixed thing. Okay? So before we talk about previous section on the section 3.3, we talk about what? Indefinite integral, right? What's the difference? Because in previous section, we say x squared plus 2 or x squared minus 4. When we take a derivative of those, right? This one becomes what? 2x. Both of them are 2x. Take derivative. Then when we take the antiderivatives, which is the integrals. So we say 2x against the x, take the integral, then it can go back to either here or here, right? Many other things, because the constant there. So when you take an antiderivative, then it becomes what? X squared plus that c, an arbitrary constant, right? So because that, we call them what? Indefinite integrals. Because it's not definite, just one thing. Okay, because the c can be 2, can be -4, can be, 2/3. So we call them, when we do the integral for those antiderivatives, we call them what? Indefinite integrals. Okay? Now, we are going to talk about area under a curve, which is a definite integrals. Let's see, what do we mean by that? Okay, so if an area under the curve, so it's like this. So we are going to find the area, how big the area is. If it's a rectangular shape, it's a base times height, you can do it. What happens if it's a curve, right? How we are going to do it? Okay, so calculus has a way to figure out, right? So let's see. So when we do the definite, area under a curve, we can think this way. Okay, if you do it same curve, you can do it several ways. Okay, so we start from A to B, definitely, right? In between, it's a fixed area between A and B. Okay, if we want to find the area, what do we do? So we are going to look at from A to B for the x. Okay, in that fixed area, definite area. Okay, that's your y. The curve is y equals what? F of x, right? The value of y is derived from x, so we call it f of x, right? Then we wanted to estimate the area approximately. So we can start to think this way. If I'm going to split this one to 5 parts, so, right, 1, 2, 3, 4, 5 parts. Then I can estimate, find the area by this way. Make a rectangular shape, right? So that will be, I can do that. Okay, then the area will look like this. If I do it from here, oops. Okay, those would be my arrow area, right? So if I just count here, I'm approximating, right? Then if I split it to 5 area and 5 parts, each part will be what? We say will be b minus a divided by 5, right? Or if I want to get closer, what can I do? I can split it to 50 areas. Okay, so my each part will be what? B minus A divided by 50. Is that right? Okay, so if I do that, then you can see it's our rectangular shape will be more close to the curve. So the arrow areas will be smaller, right? If I can split the thousands times, you will be, getting closer and closer to the actual area. All right. So then let's see how we are going to estimate the area. So take a look. And this one is what? Base times height. Your base is delta x, right? Your height will be here, right? That's your height. That's your height for each rectangular shape. Rectangle, right? So then you need to find out how high it is. Actually, that's your f of x. That's your y, right? For this value, that's your y. So that one would be what? So that's your y. Okay. So let's do this way. Because this is my delta x, right? And this point, if I call this point, I split it to 5 parts. So this is my x1, x2, x3, x4, x5, right? This one will be what? x1, x2, all the way to x50, the one before the b. Okay? Then, okay, you just have to be patient to actually figure out which is which. Okay, so we are talking about basic concepts of the integrals. And you may not need this to do your tests. You'll be fine. But if you want to go further study on the calculus, later on, advanced study, these concepts will help. Okay? We wanted to talk about how those integrals, come about. So this one is x1, this one is y according to x1. So that will be fx1, right? This point will be fx2, fx3, fx4, and fx5. Then for this one, here would be started from fx1, fx2. If you split the 50 parts, the last one will be fx50, right? Then think about this area. So this area is what? Base times height. Your base is what? Delta x, all the same, right? So you times what? fx1 plus delta x times what? fx2, all the way to where? Delta x times fx5, right? For this one. If you split the 50 areas, so your area will be what? delta x fx1 times plus delta x fx2, 50 of them. The last one will be delta x x50. Okay? So for the definite integral, that's why we are using these notations for the definite integrals. We do this way, okay? So from the area, we can say we split it to n of them total. All right, so if I do that, split it instead of 550, maybe 1,000, right? So my delta x would be what? From A to B, split it to n times, right? Then we started to count the x1, so the area would be what? The area approximately would be like this. Your times delta x, right? fx2 times delta x. How many of them? Instead of 50 of them to 50. Then if I have n of them, it will be what? Last one will be xn delta x. Okay? So you are learning the abstract symbols within. All right? N represent a concept. Can be 5, can be 50, can be 5,000. Okay? Fixed numbers of that. All right. And we also know the first point A would be what? X1 is your A. So your x1 is your starting point. All right. So that's a symbol we are using. And for this one, we also have a name. Is what? We call it Riemann sum. This guy is a German mathematician in 19th century. Okay, then what did he do is he used those notations to represent the idea for the area under a curve, how to estimate them. Okay, at the same time, we also write it this way, right? Remember your sigma notation, right? So you have 1 to n of them, 1 to 50, 1 to 5. I is what? 1 to n. So you do what? You do the fxi means what? fx1, fx2, all the way to n, then times delta x. You can write it either way. That's how we started the how to calculate the area and a curve. All right. So you don't have to worry about those symbols. We just wanted to talk about it. So where are they from? Okay. Then that's how we approximate the area by doing so, by using Riemann sum. Okay? Then for the definite integral from point A to point B for the x, okay, we write a symbol this way. Definitely in the known area, fixed area from point A to point B, okay, on the x time. All right, so, and this one is what? Upper limit, okay, so you write here, right, it's your upper and lower bound, okay, lower limits. of the, we call integral. Okay, that's the symbol we use. And for the function of what? F of x against x. Okay, we use this symbol, means what? Means this way. Means we are going to take the limit for the Riemann sum. Okay, so for this one, fx1 delta x plus fx2 delta x all the way to the n, okay, delta x. That's our approximate area, right? Can be 5,000, right? Then when we split it more in detail, the bigger the number the n is, then we were getting to close the real area under the curve, right? So we do this way when n approach the infinity. That's the very abstract concept in calculus, the infinity thing. Because you have to split it to billions smaller units to be able to really get close to this curve, then you find the most accurate area until n is infinitely many. Okay, so when this situation occurred and approached to infinity, then that will be your what? Real area under the curve, right? Then we use this symbol to show it. Lower limit, upper limit, f of x. All right, so you use the integral symbol to show it. Then what is our delta x here, right? b minus a over n when n approach to infinity, right? And what else we have? x1, x2, all the way to xn are those things, right? Are the x values, okay, beginning where? Beginning x1, which is 8, right? And beginning with x1 is 8, right? And obtaining, okay, other things obtained by continuously adding delta x. Is that right? So for addition of delta x. So we are talking about is what? x1 is a, right? x2 is what? A plus a delta x. x3 is what? A plus 2 delta x, and so on, right? So last n will be what? A plus n minus 1 times delta x. You learn those patterns in your algebra 154A class, right? So then what happened is when f is what? Above the x line, right? So if s, under this condition, f is, we are using right now, f is a non-negative on this situation. Okay, we just talk about positive part for now. Okay, so the definite integral this symbol is what? It's the definite integral. Okay? It's the same thing as what? The area under the curve from A to B. Okay? So that's what we are doing. This symbol is the area under the curve from A to B. From A to B. Okay? That's what we are talking about. So, it's given to you in the calculus. Okay, we say, oh, an approach to infinity just by looking at the concepts, they are same thing as the area under the curve. Then we use this symbol to do it. Okay, when we integral the f of x, then find the antiderivative, it ends up they are the same. This symbol means what? Taking the antiderivative of f of x from definite area from A to B, you will end up, it's the same thing as this. So we just give to you. In our advanced calculus, we have to prove actually they are the same. Okay? You don't see it for your class. It's just given to you. Just remember this. Okay? Actually, you don't even need to use the limits for the purpose of this class. Okay? But that's where they are started for the definite integrals. So on the bottom of your page 69, we say the discovery of this fundamental result for this one. Okay? So they find out if I take the antiderivative of f of x from A to B, I will end up with same concepts and same meaning, or as I take an approach to infinity, I have this same thing. So the discovery of this fundamental result signaled the beginning of the calculus as a discipline. And that's how, calculus, separated from physics, from chemistry, before astronomy, right? So before, all physics and math are, people would do one and do the another. They are not completely separated that much, because all the physics, they have to develop all those tools to help them to solve problems. Okay, so that would be your section 3.1 definite integrals.